Okay. So there's a couple things that I wanted to specifically go over, some couple of concepts. But is there any specific problems or questions that you guys wanted me to go over for sure?
Well, I believe you this last time for this one, but maybe we can work back a little more problems.
Yeah, so I kind of wanted to essentially do that where I'm gonna, because some of the homework problems kind of cover the same topic. So I want to just kind of talk about the thing a bit, and then we can go over the homework problems that cover that.
I guess my question or request would just be like I'm having trouble with setting up the equations like after I read them, like knowing how to set up.
Okay. You guys want to start with the math stuff real quick, or start with the concept stuff? Okay. Do you mean like these ratio ones, or
Okay, like I know like
the
number one talking about luminosity and I know how to set that up somehow. The same 4, 5.
okay. So the 1 and 5 are kind of two different types of math problems. One is a ratio problem. So you're given things in comparison to something else, right? So we're given star A and star B, and we want to know how things compare between these two. So this is a ratio. And then 5 is more of like a dimensional analysis problem where you're looking at your units. So for 1, we can tell that it's a ratio problem because we've got two different objects that we're comparing. We're comparing star A and star B. So are you okay with just star A? Like walk through how I would set this up. So when I don't really know what to do in a problem, the first thing I always write down is like, what do I know and what do I not know? What am I looking for? So in this, I would say, okay, I know the parallax of star A. And I know that it's 2 times the parallax of star B. And then what I don't know, this problem says, what is the relative distance of the 2 stars? So what I don't know is the distance to A or the distance to B and how they relate to each other, right? So then you want to, I'm going to give you guys an equation list on the quiz. So you want to look at your equation list and say, okay, what kind of equations has the things I know and the things I don't know? So you'll have all these equations and you're going to look for something that has parallax and distance in the equation. And so that's going to look like distance is equal to 1 over the parallax. So you know that this is the one you want to use. It's got stuff you know and stuff you don't know. Yeah.
So they're going to be on the board when we do the quiz?
Yeah, all the equations I'm going to put them all up on the board. Yeah. So then for this one, to do the math, there's a couple different ways you can do it, but one way is through substitution. So you want to take your equation and you want to write a version of it for each of your objects. I'm going to write a version for object A, so that's distance to A is 1 over the parallax of A. And then the distance to B is 1 over the parallax of B. Right? I'm just taking this equation and I've done a version for object A and a version for object B. And I know for my final answer, I want to get an equation that relates the distance to A and the distance to B, right? That's what I'm looking for in this problem, is how these two relate to each other. So I've got 2 equations here. This one has all A's in it. This one has all B's. So I want to start bringing A's and B's together into the same equation. So we say, okay, how do I do that? Well, I have this thing up here that has A's and B's in it, right? So I'm looking at this parallax of A, and I say, okay, well, that is the same as 2 times the parallax of B. So I'm just going to replace this parallax of A in this equation with 2 times the parallax of B. And now, so I know that I want my final equation to have distance of B in it, right? So I'm kind of looking ahead. I'm kind of looking for something that looks like this, because I know I want to bring this in here. So I want to kind of get this on its own. So instead of just having dividing by 2, I'm going to have this be multiplying by 1/2. So 1/2 times the parallax of B. Or 1/2 times 1 over the parallax of B. And now I can say, okay, this is equal to this. Now I can plug that in. And now I have my equation that has distance to A, distance to B, and just a number in it, right? We've got distance to A is equal to 1/2 the distance to B. Yes.
What did you multiply by 100? Cancel it out.
So right here I'm dividing by 2. So I'm just gonna say, instead of dividing by 2, I'm gonna multiply by 1/2. It's just like it's just kind of a math thing you can do. If you, instead of dividing by a number, you can multiply by 1 over that number. So I've just pulled this 2 out to get this on its own. Yes?
How come, like, for B of this problem, we found that it was 4 times as bright and then multiplied by 2 because it was twice the distance, so it ended up being 8 times? How come we just are done with this and don't multiply this answer by 2?
So this is just for distance. So for part B, the equation that we're dealing with is brightness is proportional to luminosity over the distance squared. So we need to bring in this factor here, down here, and then this factor that is A is also the luminosity of A is 2 times the luminosity of B. So you're doing 2 substitutions here. Where here we're just doing 1 substitution. Does that make sense? Yeah. Okay. Right, so if I'm doing this line, I'm going to plug in a luminosity and a distance when I do this substitution step. Okay. You guys feel okay about how to set these equations up? You write out what you know and what you don't know, what you're looking for. Look for an equation that has the things that you know and the things that you don't know. Do 2 versions of that equation, 1 for each object. Then pick one of those. Start substituting to bring in some other values. And then look for a way that you can substitute this back in. Okay? All right. So the other type of math problems are these like dimensional analysis problems. So for 5, so it says, given that hydrogen fusion to helium produces 10 to the 18 ergs of energy per gram of hydrogen, that tells me that there is 10 to the 18 ergs in 1 gram of hydrogen. How much energy can the sun produce via this mechanism with the 2 times 10 to the 32 grams of hydrogen in the core where the temperature is hot enough for fusion? So I have 2 times 10 to the 32 grams of hydrogen. Right? So I can set this up like a dimensional analysis problem. Do my grid and use this up here. I've got hydrogen up on top. I'm going to put it down on bottom here, grams of hydrogen. 10 to the 18 ergs up here. These units, the units I have in the end are ergs, which is what I want, right? The question asks how much energy, so I'm looking for my final answer to be in ergs. This is really 1 times 10, so if I'm multiplying two things in scientific notation, I multiply the coefficients and add the exponents, so that's 32 plus 18 is Q times 10 to the 50 ergs. So it's weird because we're dealing with these concepts that you're not super used to, you know, ergs and grams of hydrogen, but the actual like math behind what's going on here is something you're really familiar with. So if I ask you, you know, given that you have 5 fingers per hand and you have 2 hands, how many fingers do you have? You have 10, right? Because you're going to multiply the number of fingers per hand by your number of hands. And this is the same thing. It's how much energy per gram and the number of grams. So you multiply those two numbers and you get your total amount of energy. Right? So we've multiplied the amount of energy per gram by the number of grams. Right? This would be the same if you have, you know, 4 crayons per box of crayons, and you have 3 boxes. How many crayons do you have in total? You just multiply 4 times 3, 12 crayons.
So would the same equation be for B?
So for B, is how long could the sun produce energy via this hydrogen fusion at its luminosity at 4 times 10 to the 33 ergs per second. So in this one, what you're looking for in the end is a time. So you're looking for something in seconds, right? So I would say, okay, I have 2 times 10 to the 50 ergs. And then it gives me my luminosity, which is 4 times 10 to the 33, right? 4 times 10 to the 33 ergs on bottom, right? Because ergs is up on top here. That gives me my units that I want in the end. I want seconds. So here I'm going to divide, right? So I divide my coefficients. 0.5, and I subtract my exponents. So 50 minus 33 is 17. Okay, so when you get these problems that have a lot of units thrown at you and the units kind of all match up, and you do this. Yes.
When we're doing those, do we have to do the box method? Or can we just...
No, you can do, this is just the method that I find easiest. I mean, you could just set this up, you know, 10 to the 18 ergs per second times, or sorry, this is ergs per gram times 2 times 10 to the 32 grams equals, do that multiplication. That's totally fine. Yep. Right here. So you want to set it up in a way that you get seconds out in the end. Right? So if I had put it on bottom, then I would put ergs up on top here, right? And I would put seconds down on here. And then when I look at my units, I've got 1 over seconds for my final units. I know that I've set it up wrong. 1 over seconds, it's like inverse seconds. So that's like 1 over seconds is per second. So it would tell me that I've got that would be like, you know, whatever, 5 times 10 to the something per second. And that doesn't make sense. We want seconds to be on top in our final answer. Right? So if you set step up, before you do any math out, check your units. Cross off everything and say, okay, am I getting the right unit on top and bottom for what I want? And then if you are not, then just flip everything upside down. Okay? All right. Okay, so you guys feel okay about math stuff?
23.
23? Okay. How long will a star with 10 times the mass of the sun and 10,000 times the luminosity of the sun spend on the main sequence of the HR diagram? So again, this is a ratio problem, right? We're comparing two things. We're comparing the sun and the star. So I'm going to say, what do I know? I know that the mass of this star is 10 times the mass of the sun. And I know the luminosity of this star is 10,000 times the luminosity of the sun, right? So this symbol is circle with a dot is a symbol for the sun. Okay? So looking at this problem, it says, how long will this star spend on the main sequence? So I'm going to be looking through my equation list for something that has time, mass, and luminosity. Right? Yep.
I'm so sorry to ask to repeat it, but the little circle next to the M.
This means like for the sun.
The sun.
Yeah. This is mass of the sun, luminosity of the sun. And then this star just means for the star. Right? So instead of using A and B, this symbol always means like for the sun. So if you see this in class, like on the lecture slides, it means for the sun. Okay? So on this equation list, yeah, you're gonna look up, you're gonna say, okay, I'm looking for something that's got time in it, because that's what I don't know. Right? Time on the main sequence. My unknown. Mass and luminosity. And you're gonna see an equation that looks like time on the main sequence is proportional to mass over luminosity. So I'm going to do two versions of this, right? I've got time on the main sequence for this star, proportional to the mass of this star over the mass of the sun, or the luminosity of the star. Time on the main sequence for the sun, proportional to the mass of the sun over the luminosity of the sun. I'm going to take, was it?
Sorry, what is the little fish? What does that mean?
This is proportional to.
Thank you.
So that means that there's some other numbers in here, but they're, so you know, like these are variables, right? These can change. So there's other constants in here that we just drop out because when you're doing ratios, they don't matter.
You know how we get points if we use units?
Mhm.
We lose points if we are accidentally using an equal sign.
Because when you get your answer, it's going to be in an equal sign, right? This, for the purpose of the math and everything, you guys can like think of this like an equal sign, but we're not actually displaying it as an equal sign just to say there is some other stuff in here. It just doesn't matter for your math. Okay. Yeah.
For that first equation above the time mass is proportional to mass of the star.
This?
Below it.
This.
Yes.
That's just a question mark.
Oh, question. And
Yeah.
that was a 2 over.
Oh, sorry. No, yeah, that's just, sorry. Yeah, that's a question mark.
Okay. Thank you.
That just says this is what we're looking for. This is our unknown. Okay, so I'm gonna take this first one. I'm gonna say time on the main sequence for this star. And now I'm gonna plug in for mass of the star, I'm gonna plug in 10 times the mass of the sun. For the luminosity, I'm gonna plug in 10,000 times the luminosity of the sun. And then I'm gonna go ahead for my own sake. Are you guys all comfortable with me taking 1 0 off of each of these? Okay. So instead of dividing by 1,000, I'm going to multiply by 1 over 1,000. I'm going to pull this 1,000 out. Mass of the sun over luminosity of the sun. And I say, okay, well, this right here, this is my time on the main sequence for the sun. I've got 1 over 1,000. And the time on the main sequence for the sun. So, if I don't give you the time on the main sequence for the sun, then you're done here. This is your answer. Time on the main sequence for the star is 1 over 1,000 for time on the main sequence, time on the main sequence for the sun. But I might give you that the time on the main sequence for the sun is 10 to the 10 years. In that case, you're going to want to plug that in here. So this down here, 1,000 in scientific notation is what? 10 to the 3, right? So this is going to be equal to 10 to the 10 divided by 10 to the 3 years. So that is, if I'm dividing, I'm going to subtract the exponents, 10 to the 7 years. Okay. You want to follow that?
What if we left it at, if we didn't give us that and we left it at mass of the sun over luminosity of the sun? You want us to bring it?
Yeah, I want you to connect this, that this is the time on the main sequence of the sun.
And then that could be it. That could be.
If I don't give you this last piece, then that's it. If I give you this last piece, I'm wanting you to plug it in.
Okay.
Okay. I don't know if, like, this is something that will be given or not. I have to double check with Dr. Bolte. Yes.
Where did that 10 to the 3 come from?
This 1 over 1,000 is 1 over 10 to the 3. Okay.
And then we do the one that's 10 to the 10 for the time on the sequence.
Yes. So I subbed in for time on the main sequence. I subbed in 10 to the 10 years. Right. And then for 1 over 1,000, I subbed in 1 over 10 to the 3. Okay. Yes.
So it'd be positive 3, not negative 3.
So this is 1 over 10 to the 3, which is equal to 10 to the negative 3.
Okay.
So you can either multiply by 10 to the negative 3 or divide by 10 to the positive 3. So.
And then that's the our answer for the whole.
Right, so the question asks, like, how long does this star stay on the main sequence? And the answer is, it'll be on there for 10 to the 7 years.
And just to check our work in terms of common sense, we know that it was less than the sun.
Right, yeah, because you know that the bigger a star is, the less time it spends on the main sequence. So if it's a bigger star, you want this to be smaller than the time the sun spends. Okay? All right. So, I'm going to talk. We all feel good? Okay about the math stuff?
Yes.
Okay. I'm going to talk about the main sequence real quick, or an HR diagram, and then we'll talk about solar or the life cycle of a star. So we show this plot in class called the HR diagram, the Hertzsprung-Russell diagram. It is a chart. This axis is luminosity. Increases this way. This is temperature. Increases this way. So it's hotter over here. means this is bluer. This is redder. You guys remember that from like the peak wavelength curves? Something that has a higher temperature has a shorter peak wavelength, so bluer, hotter, cooler is redder. Roughly, radius goes up like this. So as you go that way in the graph, radius is going to increase. And then along the main sequence, mass goes up like this. So you have this x, radius is going up one way, mass is going up the other, temperature is going up this way, luminosity is going up this way. There's a question on here that says, this is upper right, lower right. It says, where, out of the four corners, which corner or corners has the largest stars? So the stars with the biggest radius. Which of these four corners is that going to be? So upper right, right? These are the, radius gets bigger as you go along this line. So these are going to be the biggest radius. Okay? And then which corner or corners are going to be the most luminous? So I hear upper left. Okay. And then it's also going to be upper right. Because luminosity goes up in this direction, right? So everything above, you know, this line is going to be this most luminous. And then which corner or corners are going to be the hottest stars? So
Upper and lower left.
upper and lower left. That's right. So hotter is this side. So these guys are going to be the hottest. And then which corner is going to have the stars with the smallest mass, the least mass? It's lower right, right? Mass gets bigger along this way, so smaller is down here. Okay, so I'm going to try to be clear when I talk about, when I say bigger, it can be kind of confusing because there's more mass and then there's larger radius, and those aren't the same thing. You can have something that has a really large radius that doesn't have very much mass. I'm gonna have to switch over this in a minute. Like mass is like how much something weighs. So if I have like a really big ball of styrofoam and a little ball of lead, that styrofoam ball is gonna have a bigger radius, but it's gonna have less mass than this ball of lead. It's not gonna weigh as much. So when I say bigger, I'm gonna try to always mean radius and say more massive if I'm meaning mass. Okay, so on this diagram, I'm going to put our stars. So along here, getting smaller as we go down, this is the main sequence. These are all stars that are burning hydrogen into helium in their cores. That is like the definition of the main sequence. So these are all different stars of all different sizes, and every one of them is burning hydrogen into helium in their cores. And the star starts out in its spot on the main sequence, and it stays there for however long. You know, our sun is there for 10 to the 10 years. These guys stay for longer. These guys stay for shorter. And we calculated some guy up here is only going to be on for like 10 million years. This guy's here for 10 billion years. These guys are here for even longer. So it's born in that spot and it stays roughly in the same spot for that whole time while it's burning hydrogen into helium. And then when it's done burning hydrogen to helium, then it moves off kind of in this direction. So up here, big radius, you have your red giants. And then down here, these are the white dwarfs. Okay? So some of these questions talk about just the main sequence. Some of them talk about the other parts. So there's a question. It is question 11. Which of the following statements are true and which are false regarding the main sequence of the Hertzsprung-Russell diagram? So we're just looking at this part right here. And it says it is a mass sequence that starts with the low mass stars at the low temperature, low luminosity corner and high mass stars at the high temperature, high luminosity corner. And that's true, right? Here we've got low temperature, low luminosity, low mass, high temperature, high luminosity, high mass, right? Is the sequence of stars that are in equilibrium fusing hydrogen to helium in their cores. That is like the definition of the main sequence. That is what it means to be on the main sequence. You're fusing hydrogen to helium in your core. Stars start their lives in the cool temperature, low luminosity corner and evolve along the main sequence as they age and get hotter. That's false, right? They stay right about where they are the whole time on the main sequence until they're ready to move off. And then once a star is on the main sequence, it stays there for at least 10 billion years. Is that true or false? That's false, right? If it's bigger, if it's more massive than the sun, then it will stay there for less than 10 billion years. So one thing to note is there are a lot less really massive stars than there are like normal and medium-sized massive stars. So you just have tons more of these low mass stars than you do high mass stars. They're just a lot less common. Yes.
What you said about if it's hotter than the sun, it's going to be there for what amount of time or something.
So if it's more massive than the sun, it's going to be there for less time than the sun. If it's less massive than the sun, it's going to be there for longer. So he talks about these massive stars, he calls them like gas guzzlers. So they have more fuel, but they are going through their fuel so much faster. So they spend less time here on the main sequence. These guys down here are really efficient. They have less fuel, but they burn it like really slowly. They like ration their fuel out and they last for a really long time. Yeah?
Can you borrow this really quick?
Yes. On the outside. So this is surface temperature. That is important. The surface temperature, when we talk about core temperature, that's going to be different. Okay, but when we're looking at a star, we can really only measure the surface temperature because that's all we can see is the outside of the star. So we can tell through just theory what the energy is going to be. Okay, I'm going to